Polyprotic acids, poly meaning many, have more than one ionizable hydrogen or proton. So if you take a look at the formulas for all of the acids in the table here, they all have at least two ionizable hydrogens. So for polyprotic acids, that first hydrogen will ionize relatively easily. And if you look at the values for Ka, you can see that some of these are going to ionize better than others. But if you compare them to Ka2, which is the Ka for the second hydrogen or proton ionizing, you see there's a big difference here. In this Ka, we can see that that first hydrogen is going to be pretty ionizable compared to that second one. And so for most polyprotic acids, we'll really concern ourselves just with Ka1, since the Ka2 values, those second hydrogens, really don't ionize very much anyway. Now we'll move on to bases. Bases, you know, are substances that produce hydroxide ions in solution. A weak base is actually going to react with water, in this case ammonia, the weak base that we always want to remember, has an unshared pair of electrons on the nitrogen. This is necessary for a substance to behave as a weak base. And so ammonia in water will attract a hydrogen off of a water molecule, and that hydrogen will come and park itself on that unshared pair of electrons. And this is going to give us an ammonium ion. And what's left after that hydrogen or that proton is removed from the water molecule is the hydroxide ion. And so we learn the definition of a weak base, or I should say bases in general, is that they are proton acceptors. And you can see then how ammonia then will accept the proton or the hydrogen ion from water. And since ammonia is acting as a base, then water in this instance is acting as an acid as the proton donor. And once the base has accepted the proton, the new species that's formed is known as its conjugate acid. So ammonium in this instance is the conjugate acid. And once the acid has donated its proton, the remaining species is known as the conjugate base. And so we would write the equilibrium expression the way that you're used to, except that since we're looking at a base, we're going to be solving for the Kb, or the base dissociation constant. And so we'll be able to determine the pH of a solution when it's a base by using the Kb and the hydroxide concentration. When we looked at acids, we looked at Ka and hydrogen ion concentration. For bases, it's going to be the Kb and the hydroxide ion concentration. So all of these are weak bases, and notice that these are all amines. They all have an unshared pair. They're all neutral molecules with an unshared pair of electrons on the nitrogen. And when we write the equilibrium reaction for a base, we do include the water, because the water does donate the hydrogen ion or the proton and ends up forming hydroxide ions, and that's how these species behave as bases. And so we would include water in the equilibrium reaction, of course not in the expression. So if we wanted to calculate the pH of a solution of ammonia that is 0.15 molar, this is how we would write the reaction. Ammonia plus water gives us ammonium ions plus hydroxide ions. And then we would put that into our expression with the products over the reactant raised to the power of the coefficient, again omitting the pure liquid water. So if we're starting with 0.15 molar solution, we know that that's going to decrease by some amount. We'll call it X. And the ammonium is going to increase by some amount, as is the hydroxide ion concentration. So at equilibrium, we'll have a value for X, X, and 0.15 minus X. And if we write the Kb expression, we have K B is going to be equal to products over reactants, raised to the power of the coefficient. We have x squared over 0.15 minus x equals our KB, which is a value of, and so our KB value was given to us in the problem, and if you notice having 0.15 minus x in the denominator here, if we are to solve for x with it set up this way, we're going to have to use the quadratic formula to do that. Now, since our value for KB is so small, then we can make the assumption that in terms of sig figs, this minus x is really not, there's not going to be that much dissociation going on. And so this minus x value is going to be relatively small. And so if the percent ionization ends up being less than 10%, then we can go on the assumption of getting rid of this minus x and just solving for x that way. At the end, we'll have to check and make sure that our assumption was correct. But a good rule of thumb is that any k value with that is going to be 10 to the negative fifth or smaller is going to be considered negligible in terms of sig figs. And so in solving for x, then we get a value of 1.6 times 10 to the negative third. That's giving us, because this is a basic solution, that's giving us the hydroxide ion concentration. So we'll take the negative log of that value, which gives us the POH, and then 14 minus the POH will give us the pH of 11.2, which does reflect that the solution is basic. Always remember to check yourself, see if those answers make sense. This table shows you the Ka values of some acids and the Kb values of their conjugate bases. And the relationship between Ka and Kb is the product of them is equal to the ion product constant of water, 1 times 10 to the negative 14. So if you know one, you can always calculate the other. Most salts are soluble and therefore are strong electrolytes, which means when they go into solution, they're going to completely dissociate and just be in their ionic forms. And so those ions can react with water to form hydrogen or hydroxide ions. This is a process known as hydrolysis. We learned in a previous chapter that anions, or negatively charged ions, are going to behave as bases in solution. Now you know that the name for that kind of reaction is a hydrolysis reaction. So fluoride ions, the conjugate base of hydrofluoric acid, a weak acid, in water, then will attract hydrogens from the water molecule, producing hydrofluoric acid, and what's left after the water has donated its proton is the hydroxide ion. So in this type of reaction, our anion is going to be our base. The water molecule is going to be acting as an acid. The cations, or positively charged ions, reactions with water, like ammonium, has an ionizable hydrogen, and so it will act as an acid and lower the pH of a solution. And of course, we learned this before too, that metals in solution, also in water, tend to behave as acids. And the way the cations create an acidic solution is because the positive charge on the cation is going to be attracted to the electron density on the oxygen of the water molecule and pull those electrons in this direction, which basically leaves these hydrogens kind of hanging out here a little bit, which makes the solution a little bit more acidic. And it's important to remember that the cations that are either smaller or have a bigger charge on them are going to be the more acidic ones. Ammonium is the conjugate acid of ammonium hydroxide. And remember, ammonium hydroxide is a weak base. So for a weak base, its conjugate acid is going to be somewhat stronger. Anions that are conjugate bases of weak acids, like acetic acid, are going to cause an increase in pH or be basic. Weaker acid, somewhat stronger conjugate base. But remember, in both instances, the conjugates of a strong acid or a strong base are not going to change pH at all. So a few rules to keep in mind. The first one is that the anion, that's the conjugate base of a strong acid, will not affect the pH. In other words, if we're talking about a strong acid like HCl, hydrochloric acid, the anion, or the conjugate base of that, is going to be the chloride ion. And since this is a strong acid, the conjugate base will be negligible in terms of pH, so it's not going to affect the pH. The second rule is that an anion that is the conjugate base of a weak acid will affect the pH by increasing it. So let's see, conjugate base of a weak acid. Weak acid, how about acetic acid, whose conjugate base is going to be the acetate ion. And since this is a weak acid, its conjugate base is going to be somewhat stronger, and so since it's behaving as a base, the pH is going to go up. And finally, a cation that's the conjugate acid of a weak base is going to decrease the pH or make it more acidic. So an example of a weak base would be ammonia. And the conjugate base of ammonia is ammonium. And ammonium has ionizable hydrogens, and so therefore, since this is a weak base, the conjugate acid is going to be somewhat stronger, and with that ionizable hydrogen will decrease the pH, making it more acidic. If we're talking about cations of strong bases, for example, sodium hydroxide is a strong base. The cation of that base is the sodium ion. And so presence of the sodium ion then, because this is a strong base, the conjugate acid of the strong base is going to have a negligible effect on the pH. And we talked about this one already too. Other metal ions that are not the conjugate acids of strong bases then will cause a decrease in pH. So most metal ions, or many metal ions, are going to act as acids in solution unless they happen to be the conjugate acids of a strong base. And whenever we have both conjugate base of a weak acid and conjugate acid of a weak base, then which way are we going to go? Is it going to be more alkaline or basic, or is it going to be more acidic? Well, it depends on the magnitude of the Ka or Kb values. If the Kb value is greater than the Ka value, then the substance is going to behave, the solution is going to be basic. And the opposite is true too. If the Ka is greater than the Kb, then the solution is going to be acidic. Oxyacids, which have a hydroxyl group that is bonded to another atom, the rule for acid strength there is the more electronegative that atom is, the more it's going to pull onto the electrons in these bonds here, and so this hydrogen is going to be more loosely held onto and more easily ionizable. So the more electronegative this atom is, the easier it's going to be to let go of the hydrogen, the stronger the acid's going to be, or the more acidic. And the more oxygens you add, the more loosely those hydrogens are held onto and dangling out there and more easily ionizable, and the stronger the acid. Another group of acids you should be familiar with are carboxylic acids, and they have a carboxyl group in their compound. And you're familiar with acetic acid. A couple of other examples are benzoic and formic acid.